Good evening, everybody, and welcome back to this stream or this video. So tonight we are going to work on bench, so a lot of Rust and less assembly than usual. Just a bit of context, if anybody is still wondering what we are doing. We are working on a virtual machine to compute activation function in as fast as possible way. So activation functions are basically just your simple mid-school functions like y equals f of x. So we need to compute them, and we need to compute, like, we have a dozen of them that we are interested in, and we need to compute them in a huge number of values. And as they are really simple function, we are computing them in tensors, because tensors are the primary object that you are working with when you do neural networks. And tensor can be complicated with geometry and stuff, but in this case we just need to apply one single function to a lot of numbers at the same time. So we can just see the tensor as a big slice, and we are going to apply our activation function to each element in the slice. So there are about a dozen of activation functions that we find interesting, and yes, hello Gilam, and so the point is today, and I'm lost. The point is to we managed to implement like 6 or 7 of them with a relatively small set of relatively simple operators, and now I would like to know if this is completely stupid, or if this bench well compared to the naive implementation. To be honest, even if it's not super competitive with Rust, it still is interesting because the half precision support is coming, and the issue is with half precision is that we do not have a Rust support, a good Rust support for half precision. So in that case, what we are currently doing is we are converting to F32, doing the computation, and then converting back to F16. So this is a really bad way to compute these. So in that case, on architecture that actually support F16, it's very likely that our new approach will be competitive. But even on F32, I'm pretty convinced it will be quite good. Anyway, so let's try to do some bench in Rust. And to do that, what I'm using usually is something called Criterion. Yes, but not there. Linalg and cargo bench. So here I'm going to run the benches on my PC. So we are situated in the linalg crate. Linalg is a misnomer, but everybody does the same misnaming. Everybody called this linear algebra, even if there is a bit of linear algebra when you do matrix multiplication, but basically it's where you put all the routine that you will need to do other computations. Wow, hello. So what's the architecture I'm targeting? So I'm targeting multiple architectures. The main one, the one for Sonos, the main one we are interested in is ARM 8, and ARM 8.2. So the F16 is relevant. We have a mix of device in the wide. Some are ARM 8, some are ARM 8.2, and we also have a couple of old devices on which we do support voice, which are implemented with Cortex A7 and Cortex A9. So we also need to do an ARM 7 implementation of the VM if we want to go all the way. I'm also somehow interested in Intel because Tract is used by other teams than Sonos, and so it's still it's better if the library is competitive on Intel too. So on Intel, my plan is to start with kinda low expectation Intel, so that would be AVX2 with FMA, fuse, multiply, and diode. This is a very common configuration today, and then I hope that somebody will pick it up to do the AVX 512, because I really don't like it at all. I don't like Intel, and AVX 512 is kind of brain fuck. The main architecture, the one we are targeting, the main one is ARM 8 with a bit of ARM 8.2, we have a Rust fallback implementation which will work everywhere. Okay, so now the compilation is done. So the fallback implementation, the fallback implementation will work everywhere and will offer us decent performance. So let's try to focus. Let's try to stop this. Yeah. So we have the fallback implementation in Rust. I can show it to you. It's in SRC generic activations. So that's the main function. So it takes this is a program that we actually want to execute. These are the X value that we are going to compute. So we have a vector for the first element and len, because this function mimics the C interface that we are using for the assembly kernels. So these are the list of nano operators that we need to support. And we have 3 registers, A, B, and C. The framework is responsible for putting the input in A. So the implementation here is a bit wrong because it will operate on, it will not split the data in chunk. It will just allocate A, B, and C. A is already pre-allocated, but it will allocate B and C in the same size as A, and it will just go through the operator and perform the operations. So that's the generic fallback. The the assembly implementation actually chunks the data so that it fits in registers, in SIMD registers on the ARM 8 chip. And perform the operator on this chunk of data, then move to the next chunk, load the data, perform the operator, move to the next chunk, etc., etc. In our assembly kernels, nope, not here. ARM 64, ARM 60, no, not Apple. ARM 64 SIMD. ARM 64 SIMD activation. So in the ARM 8 assembly, so you can find a jump table with all of the operator that this is not it. Actually, the real jump table is generated here. Oops, it's generated by this, and so it has an entry for each of the small operator, nano operator that we need to support. And for instance, if we look at a typical move B to A, you can see that we are using 8 instructions because we are actually, I mean, each register of our VM maps to 8 registers in the vector unit of the ARM8 chip. And so each of them contains 4 single precision values. So this operation operates on 32 values. And so this is why the kernel is called F3232N, because it needs to work on a multiple of 32 values, which is fine because most of the time the tensor will be in the thousands, so that's it's not a problem. It's not a scarcity problem. Anyway, so our bench is, what do we want to compare? If we look at, if we maybe look at our functions, well, ReLU is a very stupid one, but these are basically the 1, 2, 3, 4, 5, 6, 7 easy one that I called block-1 because then we have other functions which are a bit more complicated to compute. I mean, the one I'm the most interested in is this one actually, hash. It's hard switch, not hash switch. Hard switch. Nope. Cancel. Edit. I don't know why GitHub makes this so small. I guess it's because it's supposed to be comments and so be small, but maybe that's me who always want to make big comments. Anyway, so hard switch is one of, I mean, I'm interested in the other ones, but to be honest, this one is relatively hype in the neural network field today, because it has good properties in terms of learning, and also it's relatively easy to compute. So there are 2 multiplications plus simple stuff, addition, min, max. So that's very, I mean, it's a good compromise. Okay. And so these functions, we have several implementations of them that we can bench and compare. We can do, we already have somewhere, and maybe we will do it again. We can have a simple Rust implementation of them with a basic for loop. We have the generic kernel in Rust that I show you, that I've just shown you, and we have the assembly on ARM64. And I'm going to bench. I mean, I'm going to start working on Intel, but as soon as it starts to bench, we're going to move to a device, to ARM64 device. I think what I have available is a Raspberry Pi 4. I need to compose with distant single board computers. So we can use a Raspberry Pi 4. Yes, that one should work. Raspberry 4 Cali Paris. This is unexpected. It's Raspberry Pi, so maybe nope. This is going to be cumbersome if I don't have the Raspberry Pi. What is happening here? I should have checked that before. Anyway, we have another option, which is to use the laptop on which I am streaming, which is a M1 Apple. So it's also ARM8 and actually ARM 8.6, I think. So it has support for for what we want to test. but it's a shame that my raspi is not letting me connect. Let me try to add a couple of keys. Already plenty of them, actually. But yeah, I think that one is missing. So let me just, I'm going to do that in a different session. It didn't pop. Didn't show. Okay, this is the one I wanted. So now let's go back to Tsar. Yeah, fascinating work today. Okay, let me test if I can connect with this key at least. Then we'll sort out the some mess with Tmux. Ubuntu at raspi 4 Kali Paris. Still no cigar. What the what? I don't want to do that on stream. So let me check if I can see what's wrong. What is wrong with you? What is wrong? Okay. So it's not Raspberry Pi 4. So what do I have? What else? I have so many of these devices all over the place. I'm sorry for this. I mean, a Raspi 3 would be nice. But okay, I have something we can work with. I have a Raspi 3. So let's go back there and see if we can connect to Raspi Kali Laval. And we need to connect as Ubuntu. Okay, we have a device. Good. Good. So with this, let's look at Dingy. So Dingy is the tool that I'm using. It's also something that we developed with my colleagues at Sonos, and which I'm using to move code around so that I can compile on this powerful PC and then just send test or benches to this device while getting the same, basically the same command line as cargo. I'm adding dingy -d, and this is the device I want to target. Hopefully it will pick this one, device Laval, so it looks pretty good. I'm gonna check that it's the right one. I should really have done that before, I'm sorry. So it picked Laval, and yeah, that's the one. So we should be all set up. And yeah, so that's it's trying to compile some AVX 512 code, which will not work. So maybe that's something we should look into. Okay, Linux benches Intel, so that's okay. It shouldn't even try to compile them. So let's try to fix this first. So Intel harness. So I need, yeah. So by default, these all of these benches are activated. So I'm adding a bench on all the benches which are a bench equals false, so that they are not picked up by default, and I need to do that on all the benches which are platform dependent. So this one requires ARM64, this one obviously need Intel, so it shouldn't be tried anymore. So the little issue I have with this specific Raspberry Pi is that it's like 600 kilometers from the PC I'm working with, so we are going to pay for a bit of latency, but I guess it will have to do for today. Benches, what do we have in benches? And we also need to remember that we already did something like in maybe session 3 or 4, we already tried to do some benches, so we have something to start with. Yeah. So definition is, so we need to, I mean, this code is probably broken. So here we are comparing, so reference, what is reference? So crit accepts what? Yes, okay, I know. So the crit function here accepts two things. The first thing is reference function, so that would be the activation function as written in naive Rust, so no explicit vectorization at all. And this is a pointer to the actual program in the VM. So if we want to look at what it looks like, this part will be in frame, activations, definitions. So this is a program for ReLU, it's very simple. And the hard switch, for instance, that's its program, which is a tiny bit more complicated, especially this weird way to build the 1/6 and 1/2 value, which I'm not very proud of, but it does work. That way, this code was comparing here the reference implementation. That would be just plain Rust code with a loop which is here for x in v. That's the main loop. It was comparing this with a previous version of the VM that was processing one element by one element. So again, for x in v, v being the input vector, I guess, created by this call here. And this was testing the vmvec, so the Rust code that we checked in generic. I mean, it wasn't in generic at that point, but we moved it to generic and we changed it a bit, so it's not exactly the code that exists today anymore. So we can start from this, but yeah. Now I will want to compare the reference implementation with the generic virtual machine, so the one implemented in Rust, and on platform where it is available we want to compare with the Rust implementation. Okay, so it looks like Dingy is working. It managed to run a bunch of tests. I mean, these are benches actually. I mean, these are tests, but benches has to ignore the test. And so, yeah, so it's working. We can work like that. It's fine. So I'm going to grab this test, this bench as is, and going to fix it to work on, to work with the new constraints. So it was in activation. I think it's the last bit of the temporary activation folder that we haven't integrated in linalg already. So I'm moving this to benches, activations, .rs. I need to declare the bench. So I'm going to pick it all the time because I will try to make it work on all the computers, on all the architectures. And let's run the bench on the PC. I mean, it will not even compile. Yes. Okay, that's fine. So let's fix it. Finally, getting into code. Benches, activations. Okay, so these two ones I'm gonna ignore for now because they are not part of the block-1 of the easy one. Exponentiation needs some specific operator, and same for sigmoid. So for now we'll focus on these two guys. So I will keep the reference implementation, and I'm going to try and fix this one first. Up. But I need to import it from tract linalg frame activations. Okay, so program is probably not called that anymore. So it's in activation. Actually, there program. It's already imported. So what's wrong with this? Yes. I need to make it. It became generic in the meantime, and we need to specify which of the which side we want to focus on. Okay, the rest is basic criterion code and usage. So we are creating a name for the bench. For the name comes from here. It's actually the name of the activation function. This list is a list of size for which we are going to try to run a bench. For now, I think we will focus on 1000. You don't see my screen, damn. It was not intended. Okay, back. Yeah, I mean, and it's been like that since the beginning, I guess. That's just great. That's just great production. Okay, it was one button away. I just needed to. Okay, sorry for that. Okay. Well, I mean, at least you haven't seen any of the SSH manipulation and stuff, I guess. So anyway, cargo bench. So I mean, it looks like it's not compiling here. If you import a switch, refer to it directly. What's wrong with this? So this one works, that one doesn't work. Pretty sure I just did something stupid like this. Yes. I've changed the name in the meantime. Okay, so let's do the first bench on the PC. So prog is unused, yeah, because we are just doing the reference implementation. So the one with the loop here. That way I can repeat all I explained before. Okay, here we go. Okay, so we have first we have here first number. So like on this PC, we are doing. I mean, the one with just one element is a bit stupid. You can see that we are gaining some performance. I'm just going to check that. Yes, we are setting the throughput correctly. Yeah. I'm curious. I mean, yes, the actual. I mean, as I was saying before, the implementation do not iterate over chunks, but performs on the. Oh no, it's a 4 actually. It's a simple one. So this one managed to speed up for some reason in between these two sides. I'm not too sure why. I guess we must amortize something related to memory. And another interesting bit is there is little difference in the performance between ReLU and now we are moving to something else. In ReLU and hard switch. Like here we are at 3.2, here we are at 3.2, 3.5 and 3.5. So as the two operations are different, I mean, as the two implementations are a bit different, then I mean, what it means is that we are probably memory bound with this operation on Intel. It could be the same on on ARM. Anyway, so now what we are going to do? We are going to use this to run. So that's so now we want to run the virtual machine. So I'm trying to figure out. But no, I mean the right bit. I mean this one, the implementation of the virtual machine in scalar mode, so it's not super interesting. So we are going to do that, and I need to grab my virtual machine implementation. So I'm going to call this one generic. And I need to pick the VM. So to access the VM, I will go. I mean, this is not how it will be used in the end. I mean, when integrated in Tract, there will be no direct access to the implementation. It will go through I mean, kind of smart virtual table to pick the right implementation. But for now, we are going to do it like that. So I'm going to go to linear generic activations, and I'm going to pick S activation. And I want this to, let me try to remember the interface, because yeah, it's a bit complicated, GLAM, but it's also complicated for me. So no, I'm going to frame. No, that was fine. Frame activations.rs, and I'm looking at. So what I'm getting is what I'm getting with this S activation. So S activation implements activation kernel, which essentially essentially implement this run function that will operate on a slice which is of a size which is multiple of 32, 32 being forced by this guy. And we are calling the act function on this to get the high-level interface that can actually works on any buffer and will take care of chunking in 32 and also aligning if it needs to be aligned. So for this I need to so S activation is an activation care, right? I hope it is. Let's check generic activations. So it should be defined here. S activation implement activation care F32, so that's fine. And so we can, so this should work, but S activation, yes, it's a struct, so come on, you should find it. I mean, it's in the trait and you implement the trait. So what's wrong now? Okay, method not found in S activations, no method compute slice. Yes, that's for after. So what is happening here? Why is it not working like this? Activation care F32 for S activations, and activation care does have the act function. Should I maybe, yes. Okay, yes, so I was using the dot. So the dot is calling an instance method, and this is a static method, so I need to use the double column syntax. And now it says that I need to just get the trait in scope. Okay, here we are. So now we have a box din activation F32. So this is the high-level interface to which I can pass a buffer with regardless of its size and alignment, and the function will chunk it and pass it to the, I mean not chunk it, but make it a nice 32 multiple size and send it to our kernel. So now I can call vm.run, vm.run, yes, that's right, and first comes the program. So the program we have, and the vector will be v mutable, and yes, so that should be generic. And what I'm going to do also is, let's declutter a bit the screen. I'm going to add a prefix to the benchmark group, to the benchmark name, so it will be activations. That way I can, well actually, no, that was useless, because what I can do is I can do it like that. So now we should get on a PC the two. We should get the two implementation, the one with the for loop, which is right there, and the one with generic kernel here. Okay, so on one single element, it's not a big surprise that our VM is not great. On 32 elements, let's see if it's better. It gets better. So here we are processing 1.2 billions of elements per second with the for loop, and the VM is like 20% as fast. But if I remember correctly, at around 1000, it was getting better. So reference on 1000, 2.4 billion per second, and yes, that's it. The generic implementation is now faster, and with 8000 element, it should be yes, even bigger. Okay, so that's with the Rust implementation. So now what we are going to do is we are going to add a bit of code for the ARM64 kernel, and we are going to see how it behaves. So let's do this for now. So I'm going to do something like that, because the VM has a name actually, so I can do it like this. Is it compiling? Cargo, check, benches. Yes, so act doesn't have names. We'll fix that because I need a name for many things. Frame activations. So activation is here, and I'm going to add name. So the idea is so kernel is static, but the activation is dynamic, and we are calling we are using dynamic invocation on the activation on the high-level interface. Okay. And so I will need to fix right away the implementation. And I'm going to call k.name, k being the underlying kernel. Okay. So that way this code should now compile. So there is a bit of layering here, because we have activation is the high-level trait that the other crate will be able to call. Activation implementation is the implementation of the trait, and it's parameterized by an actual kernel, and T is the element type, so that would be F32 in our case, and that's good. And then, okay, so this is a box. Let me try to get a bit more. Yes. So this act function return a box of the activation trait. So this allow me to to add more elements, to add more variants. So let's say we're going to make a vector of them, and here, so we make it plural, and for VM in VMs, we are going to run this bench. So I'm using the VM name here, so the bench will be unique. And what I'm going to do now is I'm going to make a conditional section. So if target arc is ARM64. I think that's right. I'm going to add tract linalg ARM64, and now the completion will break because it doesn't know, it's not smart enough to follow me there, but that's okay. This is what I want. ARM64 ActF32, so that's the equivalent of as activation, and I need to call act to get my box dynamic. So let's fix the typos. And let's see if raspi, right? What? Yes, I just did a check. So, well, at least we know it compiles. But now we are going to run the bench. I mean, the Rust code is not super difficult. What makes it difficult here is that there are lots of macros plus a lot of conditional compilation, and on top of that, I'm lazy, so I tend to write macros when basically sometimes I should just write the code two times or three times, but I don't like to repeat code at all. So that makes it complicated. And it's also a bit of an issue because people who are trying to help in the project are struggling, and I know about that. I mean, some make it because a completely non-Sonos team provided implementation for the matrix multiplication on AVX 512, which is something I had really no professional or curiosity motivation for. So it's good that they at least managed to do that. Let's try if we can fix this warning. So it's unused mut. So this happens because on Intel we never mute the vector, we only mute it on ARM64. So the editor doesn't know about this section. So we need to allow this to avoid the warning. And hopefully, I mean, what I should do really is I should specify which bench I want, or else we're here for quite a while. So here we should get Relu and Artswish. We can add the other because it's, I mean, everything is already plugged in, so it should be pretty easy. Soft sign would be interested because it had this division thing, which is super expensive. But beyond that, I mean, I put bench on the map for today, but given that we had already done it, it went pretty fast. What I could also do is run the bench on a Mac M1 machine to see how it goes. What okay, so this is, so yeah, we are on a, so this is a Raspberry Pi 3, so totally different kind of machine. So before we were looking at figures in the hundred of millions or in the billion of elements per second. But here we are running on a Raspberry Pi. So different experience. And we have, yeah, a good thing is we have our three implementations. So that's for, I mean, the scalar one, really, I should skip it. It has no point at all. 32 is still a bit kind of pointless because in between, I mean, in 32, we need 32 elements consecutive and aligned the right way. So we are probably moving them around, but with 256, it should start to be more interesting. So the reference is 178 millions. The generic implementation is slower at 90 million of elements. And while the VM is slightly slower than the reference implementation. But ReLU is a very dumb thing, it's just max with 0. So generic gets faster at 200. In reference, a generic, so now reference and generic are in the same ballpark. And now the VM is better. Okay, so even on ReLU, it's interesting. Reference at 230 million, generic at 250 million, and optimize at, yeah, no, that's good. It's twice faster. It's not super fast, to be honest, because ReLU is just max with another element. And so we should be able to do 4 of them per cycle. And 4 of them per cycle because we should be able to issue one of these instruction, this vector instruction per cycle. And this Raspberry Pi 3, if I remember correctly, it's at 1.2 gigahertz. So the max CPU speed should be in the 2.4 gigahertz. Except there is memory, which, I mean, we are still probably paying a lot more in memory access than in actually doing the computation. ArtSwish at least has 2 multiplications, so it might be a bit more interesting. But I mean, still, it's still pretty good. I mean, speed up of 100% or so, I mean, even a bit more. I take it. Given that in the end, I mean, it will not make tract significantly faster because really, when you compute a neural network, the only thing that matters is matrix multiplication. The rest is just peanuts. So it's over engineering here, but kind of fun. I mean, it's my kind of fun. Where are we? 1000. Oh, so at 1000, the reference implementation is actually still. So let me try to stop scrolling and have the 1000 on screen. So will I manage it? Yeah. So this is a reference implementation. This is a generic implementation, and this is the assembly implementation. So in that case, we are slower than the reference implementation. Huh. That's interesting. It's not great news, but it's interesting. With 8K elements, we are the same kind of speed, 230 million of elements per second. Okay. I'm going to I'm going to try it again, just because I'm a bit cautious with these. Art swish. Let's see if I can run. I would like to run all the 1000, but I cannot use. I mean, I can set a prefix, but I don't think I can use a star to say all that start with art swish and ends with 1000. So there is a lot of variability in the small values. So where are we now? So art swish, yeah, art swish with 1. Completely non-interesting. I'm really curious why the 1000 case, why it takes so long for the art switch to be better than the reference implementation. It means that at some point we'll have to look at what the compiler is doing with the reference implementation. The thing is, on ARM64, it is a given that it is a given that the SIMD unit will be there, and so Rust can actually generate code that will use the vector capacity of the chip, and I think it does actually, which is why it's the reference implementation is actually not too bad. Compared to the uncrafted one. Yes, so we are still a bit lower. And there is something else. Our implementation actually has quite a bit of overhead because it's an interpreter. We have this main loop. I mean, yeah, we have the main loop where we loop over chunks of data. And then inside this loop, we have a smaller loop on which we are iterating on the various instruction. But since it's an interpreter, we need to fetch the instruction, we need to decode the instruction, we need to run the instruction exactly as if we were implementing a processor. And so we are jumping around the code and we are doing a bit of a bit of overhead, I mean a bit of branching and deciding what to do next. What we could do, which I think I put in the last item of the to-do list, is instead of using an interpreter, we could actually compile these functions. So that would mean that instead of having one generating function that I call with a slice of data and a program that represents the activation function I want to compute, I would have one of these kernel, which I would generate because I'm lazy, but I would have one of these, one function for ReLU that would take just a slice of data, one function for @switch that would take the slice of data, etc., etc. And in this case, I could get rid of all the jumping around code and just concatenate the implementation of the actual opcode. So basically, if we have a look at the if we have a look at these, so the outer loop is here, and it ends there. So this is a loop that loops over slices of 32 elements, and we have the inner loop here that will fetch the next instruction this is essentially the decoding of the instruction, and use the jump table, which is generated, that you cannot see here, to go to one of the actual implementation. So we have a various implementation for the moves. And here we have absolute, we have reciprocal, we have, this is A plus B to A, and this is A minus B to A times B to A, etc., etc. And so if instead of going through this decoding and jump table for the activation function, which are known beforehand. I mean, we know what activation function Onyx contains, and it's not like there are 100 of them, and it's not like they're changing every day. So we could kind of pre-compute these, and so we would avoid all the jumping around with the jump table and stuff, and decoding and bit masking and etc., etc. That could be a bit faster, but I mean that's for yeah, it's at the end of the to-do list. Okay, so I have a bench. I'm not super happy that this is not significantly faster than this one, but at least it's kind of faster, and it's working, and it's, I mean, with big enough tensor, it will not induce any significant regression. So that could be integrated into Tract. Anyway, I think that's it for the benches. The question is, I think I will tick that one when I commit. The thing is, what should I do next? So definitely not this one for now. Integration in Tract core, is it the right time to do that? So Tract core is, so you've seen that we are working in a crate called Tract linalc, and as I was saying before, that's the crate where all the low-level computing routines are put, and on top of that we have Tract core, which contains everything which is really about neural networks. So this is where we will find convolution, this is where we will find graph management, axis manipulation on tensor, etc., etc. So the thing is, I think I need to think a bit before starting that one, so probably not today. That one is super interesting, but as I cannot connect to my Raspberry Pi 4, I do not have any chip with F16 support right now, so we'll not do that. Maybe we could have a look at these guys. These two guys are interesting because I already have an implementation of them in assembly. And the point was, I mean, it's handcrafted from top to bottom. And I already have a translation of these into our VM with caveat is we need a couple of more instructions. Actually, we need one more, if I remember correctly. So maybe that's our next step, sigmoid and tangent. Okay, let's do that. Let's commit the benches. Activations. That's in benches activations. And so diff. So I've added a bench to the benches. I fixed that one. I've added the name. Okay, that's it. Relatively light session. Benches. Okay. So let's see. SRC frame. So I'm going to look at the definition of sigmoid and tangent hyperbolic in our language. So you can see that they're a bit more involved, but most of the, so I have done sigmoid, I haven't translated tangent, hyperbolic tangent, but it's more or less the same. Oh, yeah, we have changed the way the program was is encoded. So in the early iteration of these series, we were actually separating the program and the constants, but I think it was a bad idea. So now they are fused. So I mean that's going to be a bit tricky. You can actually switch these two. So max 2 is okay. Let's do this differently. I'm going to, yes, show these two, then this comes, I guess, mul constant, it has to be this one, yeah, constant 4, constant 5, FMA 6, FMA 7, FMA 8, 9, now we're moving to betas, so swap mul const, add const, FMA. So FMA 1 is actually just the value 1, and this 0.5 comes here, and I can get rid of this. So I need to fix all of these now. So that's like this. Bit of editing. Could do this faster. I mean faster, not faster. It would take me the same amount of time, if not more, but I could try and look smarter when playing with VIM and substitution, but let's keep it simple. So this guy, that guy, this one, sorry for the comment, FMA, 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 mul, add const, FMA, FMA, add const. Okay, it's not good. What's wrong? What's wrong? Something is wrong here. Oops, what did I do wrong? I removed one that I should not have removed. Oh yeah, 1.0. Okay. And so I think now I can remove that because yes, it's not too bad. So this we have, all of these we have, we need swap BC, the moves we have, even if this is a bit ugly. Move B, move C to B, then move A to C, then move B to A. Yeah, okay. Maybe we need one more swap, but I don't know. Maybe. Recip we have, move, mul, and add. So the two that we need are swap and FMA. Okay. So I think we already have them in the VM definition. It's just that we did not try to implement them. So the VM definition is here. We have, yes, FMA with T, and we translate FMA with T into FMA followed by the value T, the bytecode. We have done the jump encoding, so that is ready to work. We just need to do it. So first we're going to test. We're going to add test for swap BC and FMA. So the test, where are the tests? The tests are in activation tests. Yes. Okay. So these are the unit tests for each operation. We struggled quite a bit with them in a previous session. So their property test, and then we have so we have a mix of properties tests, one with the prop suffix, where x is random, and we have some concrete tests which are basically non-regression tests, so things that we had to fix and that were discovered by prop test. So swap BC prop. So this one is this one is tricky again to implement because it's not directly observable. So what we can do is here we are loading 2's in the register B's. We are loading 3's in C, and we are checking that the if positive then else is working. But what we are going to do is we are going to swap B and C, and we are going to move to A, because A is the only register that we can observe. So we are going to move whatever is in B to A. And so we should observe 2's. Or what I can do is, because this will kind of test that the swap has successfully overwritten all C's with B's, because no, actually I will observe 3's like that, because at the beginning we have B equals 2 and C equals 3. We are swapping them, so B equals 3, and then I'm moving B to A, so I'm going to observe the 3's that were before here in there. And if I want to do the thing right, I need also to do the rest. But what I can do is I can piggyback on the previous test that actually is testing a mix of testing the two at the same time, really. And so if I'm doing this, I'm basically just reversing the previous test, and I can look that both B and C has been. I can test that both B and C have been overwritten correctly. So it should work with the generic implementation already, because it was implemented. If I fix the code, so the code is here. This close that. Where is what is wrong? What is wrong? Load. What is wrong is this should be there. Yes, we have an indentation problem in this file, I think. Let me check. So this match that, this match these, okay. So this should be like that. All right. Here and this close this, that close this, and this goes away. Yes. We are in a macro, so the formatter doesn't follow through, and it's still not good. It's still not good. So where is the problem? Is it that? I think it's could be. Yes. So the problem is here we are in a macro that contains all the property tests because there is this word syntax or the tests. So we need to close the macro before going through the regular test, and these guys should be indented differently, and then we have back into prop test, and in the end, yes, okay, so all of this section, I will not do it, but all of this section from there should be shifted one tab to the left, I mean actually up to there. So we have the simple operator, I mean the nano operators in prop test, we have some regression test on the nano operators, and then we have the integrated test where we test full activation functions. Hard switch, okay. So this clarify that, and so my problem is in activations, definitions, 85. It's a program of 32. Okay, so swap BC on the generic implementation is working. So now, if I'm moving to a device, I should have an error because we haven't implemented it in the ARM64 assembly. But that's our next task. ARM64 act. Here we go. So we're going to fall into this guy and we're jumping to unsupported. So we should see something like kernel returns 1 instead of working. So one interesting thing in this assembly is there is no move on the vectors, so we have to use a logical instruction like this. For instance, this is a move from C to B. So so this is the destination registers, and these are the source. So A and A is A. So this actually implements a move, even if it looks a bit complicated. The thing is, the AND is as fast an operation as you could get on this device. So it's I mean it's not expensive. It's just it's a bit in the syntax. So in our case, we need to move to swap B and C. So we'll have to move. Yeah, we need to do 3 of these. First, we need to move B into the empty slot after the register 24. Then we are going to do exactly this. And finally, we'll do move CD, so the D register that doesn't exist. So this is move B C. So before doing that, I need to do move to move B into D, and after that I will need to move D into C. And after that I can do inner loop. Okay. So D is 24 to 31, and I've never used it before, so I'm just going to do it like that. 27, 28, and really VI gets in the way with the completion. 31, here we are. So this V16, this is C, so it's not correct. Okay, so we have kernel function return non-zero. So that's what we were expecting. So here, these guys, I need to replace with B's, and B's is these ones. Once, twice. Okay. Oops. Okay, so this is move C to B, that's correct. And finally, I need to move D to C. So I'm going to keep the middle column, so that's C, and this is D. Once, twice, removing these. Nope. Nope, 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 nope. Cancel, cancel, cancel. Up. There, here. Okay. Let's see now if we have a swap. Actually, I'm just going to try something. It's not ARM, it's ARC. Because I think it's going to be a bit faster to use. I mean, I have Dingy configured to either use a device or use a QEMU emulator. So for bench, it's not valid, but for tests, assuming that it does the right thing, which is what I'm testing there. Okay. So it's faster because it doesn't have to, I mean, the executable is actually pretty big, and so by just running on the emulator, and I don't need to push this big file over my semi-broken VPN and over hundreds of kilometers. All right, so we have our swap. Next one is FMA. So FMA, same principle. We're going to do a test case. So what does FMA does? FMA does, I don't remember actually, so we will check. We'll check in activation. I mean, we have the generic implementation that works, so we are looking at what it does. So FMA, where are you? It's here. So it's here. So it does. So it accepts a constant, and it does. Okay, and it does A times B plus the constant. Okay, so the problem is that's not what it's not exactly what the FMA is doing. Anyway, let's try to do the test first. So FMA probe. So in this case, we are going to need an X. We're going to get a Y which will be a constant. So it will be any TI. And we are going to need one more constant. So this is going to be our B. And we have a constant. And so we are going to load a B in B, easy. And we are going to FMA with K. And the result should be, for given X, we should return X times Y, which is B plus T. X times B plus K. So what's wrong? Let's see if we are testing. So we should see one green for except FMA. We'll see. We should see one green for the generic and one red for the assembly. One passed, one failed, and kernel function returned on 0. So our test is working with the generic activation. So that's fine. Let's do the assembly now. And it's going to happen FMA. So it does A is A times B plus T. Okay. Problem is we have VFMA. So the instruction VFMA does show, I like that it says it in English, multiply corresponding elements in the two operand vectors, then accumulate the result into the element of the destination vector. So what VFMA does is A plus equals A times B. Let's try to, no, that's wrong. A equals A plus B times C. That's more like it. Okay, so we need to work around this. So basically, we will have to move A to D again. And once A is safe in D, we're going to put nope, this doesn't work because I need one of the V24 to store so B is fine. B can stay where it is. So we need to move A in D. Then we need to multiply. Yeah, we need to move the constant in A. Move in A the constant. And then we can do FMA A, and so inside A I'm doing K plus B times D, because I moved A into D. So the problem with this is to do this, I need one of these registers from V24 to V31 for my buffer, for my working registers. So I will need to do it in 2 passes. So first, let's load the constant in V24. So that's V24 is broadcast of K. Then we are going to move the first half of A into, let's say, V28 to 31. Okay, so that's and V28 for S, V0 for S, to D. So only 4 of them, because we will need to do it in 2 passes. Okay. Then we are overriding the values with K. So, and V0 for S, I'm putting V24 for S, 24 for S. Actually, I can do it differently. I can do it in I can first move all of A to D. Yeah, that's better. I can move all of A to D, broadcast K on all over A, and then so I don't need to do it in two passes. So that's a bit better. So first we move A to D. Should I try to? Well, okay. And it was wrong anyway. There was a 21 here. That's the kind of thing that probe test is good at catching anyway. So move A to D. V. So we start at 24, 25, 26, 27, 27, and 26. 28, 9, 30, 31, 3, 4, 5, 6, and 7. And these guys, I'm reusing these ones. Okay. 0, 1, 2, 3, 4, 5, 6, 7. Then broadcast in V0s. I'm broadcasting K, so I'm inserting K in V0. I'm keeping that because that's keeping my instrument pointer to the right place. Duplicating in all of these. 6, 7, 8. Here we go. I need these ones with a comma. Okay. So this is move A. Okay. So let's get rid of these. It's already explained. And finally, we can do VFMA of A, B, and D. So let's start from there. VFMA. Yes. VFMA. Missed it. VFMA. Ah, come on, you can do this. VFMA. I'm doing something wrong with my fingers, and yeah, okay. Going to do it differently. VFMA. All right, so to A, and the operands are B and D. So D is this guy. And B is B is B is V8. Yep, these ones. FMA. And inner loop. That's right. Okay, it's not apply yet because I've picked a B that operates on bytes, and I need a B that operates on integer, so I need to replace 16B by 4S, and I think exactly the opposite here. No, VFMA is wrong, so I think I'm mixing instruction sets again. So it's V, so these are, yeah, so that's the old instruction set, the ARM v7.1. So I'm going to use once again my incredibly big PDF, which takes 30 seconds to open. And I think, I can try to find out. Okay, here it comes. PDF is ready. Let me push it on the right screen. Up. VFMA. So it has to be, it's not V, it's FMA, I guess. Ha. Big PDF. V prefix is the syntax for the old instruction set, the ARM 7.1. So I guess my best guess is we have to do FMA. Is it ready? FMA. Oh, come on. And believe me, using the PDF is difficult, but it's even worse to use the website, in my opinion. Okay, let's see. Is it happy with this? A non-mnemonic FMA is, no, it's not happy. Let's try to see FMA Advanced SIMD. FMA instruction sets, that's Intel. Advanced Neon, closer to the truth. Will it give me the mnemonics? VFMA F32. Aha! VFMA F32 with a suffix. Okay, let's try again. So, V FMA F32. Unknown meaning VFMA F32. You know what? I have been using this like hundreds of times in these, so it should pop everywhere. So that's the one which is not working. And it's not FMA. So what could it be? ARM64 SIMD. Let's go and see a matrix product, because that's all over the place in there. So naive, for instance, VI, FMLA. Okay. So fuse, multiply, and accumulate. FMLA. FMLA. Okay, so now, yes, this is I was mentioning this before. It cannot, AND doesn't operate on single precision value, but it operates on bytes. So we need to use the right suffix. And like that. So now it compiles. And it does work. Now, what we want is we want integration test, yes, for the sigmoid stuff. So it's going to be in SRC frame activations tests, and so I have one for out switch. And I'm adding a sigmoid test. So this actually, they should all be named with the suffix prop. Yes, and it disappeared somehow here. Prop because they're property test. Okay, and I'm going to use the sigmoid definition. And I'm going to test it against what? Against, I think I have yes, I have a naive scalar implementation here. Create generic sigmoid. Here we go. So I need to mention sigmoid. And we should get we will get 2 tests with activations plus other sigmoid tests, which are working on the actual uncrafted sigmoid implementation. So the one that we want are this one, sigmoid prop in activation, and act sigmoid prop is okay. All right, so that's progress. Now what I'm going to do is I'm going to add this test reference sigmoid definition sigmoid. And what I'm going to do for the sigmoid is I'm going to add another test, which is going to be the actual uncrafted sigmoid implementation to compare it to the virtual machine. So to do that, I will do a bit of code. Let's say we will define, because I need to duplicate a bit of the logic in there, so trying to not doing it too stupidly. I wish this was capable of, so it was E32, okay. For size in sizes, it won't. Okay, and the rest I'm going to, duplicate. So I'm going to take this. Yes. Fixing the size, so this will be bench with input, so I need a benchmark group. Group dot benchmark group benchmark group sigmoid. So here, yes, that's a group. So it's let group. Okay. So I already have a group called sigmoid. So it will not let me do this. So what can I do? I'm going to do it very, yeah, it's not going to be nice, but it's going to work. So if name equals sigmoid, and I'm going to add it just like that. I don't need this. And I am going to call it uncrafted. And show how should I call it? Let sigmoid equals. I need to pick it, so it will be in tracklinalg. Yes, I'm going to take the. I'm going to assume. Right, I'm going to assume that this is giving me the right implementation. No method sigmoid f32, really? Fill not a method, fine. Okay. Yes, and it's because, here we go. So I'm back to a box element wise, which actually is more or less the same as a box activation, which was here, except it doesn't need the program. So here I will call on modv, I will call sigmoid dot run and mute of v, and that's it, I think. Okay, okay, so let's do a bench on the PC. Cargo run bench, cargo bench, bench activation, and I'm interested in the sigmoid one. Okay. Yes, so that thing goes away. This is fine. So I'm expecting the uncrafted implementation on PC to be faster than the VM, because we do have an implementation, an uncrafted implementation on the PC. And which is in assembly, and so we will compare an uncrafted assembly to generic Rust fallback. So there is barely any doubt that the uncrafted assembly will win. But then when we move on ARM64, we will compare an interpreter in assembly doing the sigmoid with a handcrafted assembly that does the sigmoid, and so I'm pretty sure the handcrafted implementation will be faster. The question is faster by how much? So once again, I should really remove the one from there, because it's a waste of time. $32. So we have 3 implementation. Yes, reference, generic, and uncrafted. and you can see that on the scalar case, even on the scalar case, the uncrafted implementation is already much better than the generic, but not as good at the scalar implementation, the scalar naive implementation. But with 256, let me try to stop scrolling. So wow, the uncrafted is 10 times faster than the generic. Okay. No big surprise here. As I was saying, we are running with we are comparing very different things. So let's do the same on my Raspberry Pi. So on the PC, the uncrafted assembly still beats the generic, but not by that much. It's one bit, yeah, it's like 10% faster. Okay, here we go. Let's see. Well, scalar case. That's it. I'm killing it. So, comparing again. So with 32 elements, this again is a for each implementation. And this is interpreter fallback in Rust. This is the optimize interpreter in assembly. And this, whoa, this is the uncrafted assembly. So I think that I will keep the old Sigmoid code because the VM is not as fast as obviously and by a significant factor than the uncrafted assembly. Let's see how it pans out with bigger values, but there is no reason that it changes. So here the virtual machine in assembly is at 28 million of computation per second. The uncrafted is like 3 times faster, more than 3 times faster. Which kind of makes sense because the FMA, and I mean, it would be hard to beat because the FMA is a bit awkward to implement with interpreter because we need to do these moves around. So maybe there is something to, maybe there is something to do differently here. I mean, it's not incredibly bad, but it's a bit disappointing, to be honest. I thought it would be. I thought it would have been closer, but I mean the good thing is on a platform where I do not want to do the Sigmoid by hand. It's still better than the Rust naive implementation. And when the tensor grow bigger, it looks like there is less difference. With 256, we have more than 3, and here we have a bit more than 2. So, yeah, not super happy with this. Not super unhappy either. It's also. I'm going to commit this and I'm going to stop for tonight because it's a nice progress. So we have Sigmoid. Did I add some file? I don't think so. We're going to tick that one and we're going to edit this and say this was done part 10. And Tanche and exponentiation will have to wait for next time, I guess. Or maybe next time we'll do integration, so I will think about that. And in the meantime, thank you for watching. I'm sorry for the stupid thing at the beginning where you could not see my screen. And well, that's it for tonight. Good evening, everybody. Thanks for watching.